This is the first hour of Physics 1C for November 22nd. And tonight we're going to be talking about, or today we're going to be talking about self-inductance and inductors, which is going to be our last of the three major passive circuit elements that we've learned about. We learned about resistors, capacitors, and tonight we'll learn about inductors. The one thing I wanted to do, though, was on Friday, or Thursday, I think it was, Michael Rodriguez came and he showed me that he figured out how to take something from the FET website. I think on Friday I was trying to show you all this demo here, but I couldn't make it work. And in the time we had, I couldn't find any kind of an emulator to make it work. But Michael was nice enough to find this program that he linked me, which allows you to view anything, any URL to run a Flash program through it. And that's what I got here. So this is the demo, not demo, but the FET thing that I wanted to show you all last time that I wasn't able to show you. So we're going to start with this. Yeah, Stefan, you're not muted. I can hear everything. There are all sorts of like clicks and stuff. So you don't have to, by the way, you all know you don't have to be muted when you're in the channel. You just need to have a push to talk key enabled so that by default you're muted and that you have to push a button to talk. That's really the way you should be doing it. But everyone just is muted, so be it. Anyway, so what we have here is a positively charged particle. We've got these lines that are emanating out from it. These are the electric field lines as we know them normally. There's no arrows or anything, but the lines themselves represent electric field lines, right? They don't represent the electric field itself. They just represent a single continuous line drawn through parallel electric field vectors. So it's not a vector field that's being shown here. It is just the lines themselves, okay? And this is designed to teach you about how waves can propagate along electric field lines. So imagine this line right here, right? Watch what happens when we bump the charge a little bit. You see how a wave emanates out from it like that there? Give it a little wiggle, and a wave will propagate out like this. In case you don't know, a wave is any kind of disturbance that propagates through a medium. In this case, the medium is effectively this line right here, which acts like a string, and all the other lines around it, because you can see that these waves are emanating out in all directions, right? And this would be what we would call an electromagnetic wave. Here's a nice animation, right? And I can provide the links to this for you as well. They're in the office hours text channel, but I'll copy and paste what Michael showed me. You need the first link to view, in case for whatever reason you go to the FET website and you're looking to play around with these demos and you find one that you can't get access to, well, then you can use these two things. The first link gives you the player, and then the second one gives you this. We can do a lot of stuff with this. So we can imagine what would happen if this thing was wiggling a lot, which particles never stop wiggling. So this is the kind of waves that would be emanating out from this if it was just, wiggling up and down. You may notice that on the top and the bottom that there's really no waves coming out. Not really. I mean, there are some, but it just depends on how much I'm wiggling my hand. There you go. You get these kind of constant waves emanating out. It's very trippy. We can make it sinusoidal, so it will kind of wave up and down how we would expect for a sinusoidal wave. And you get these waves that emanate like this. There's, we can also change the amplitude, so it's not giving as big of peaks. We can increase the frequency so that it waves faster, like this. And when we do this, you can see that there's really no energy coming up and down. All the energy is going to the right and left. So if we want energy to be flowing out in all directions, we have to make it move in a circular direction. So if we do that, now we've got waves coming out everywhere. So many that it's kind of hard to see what's going on. So maybe if we slow down the frequency, we have those waves going out. Show velocity, what is that going to do? Oh, I think this is showing the velocity of the particle, basically. Okay, that's not particularly useful. Anyway, so we can stop it, and then of course we can do things like we can bump it. We can change the amplitude of the bump, do stuff like this. So I showed you something that was like this, but I wanted to show you this one because I think this one's way better, because I think it gives you a really good way of visualizing what's happening. Because if you imagine inside of a, yeah, it is kind of hypnotizing, I agree. Especially when it's on like this motion, right? I just wanted to show you this one because what you can imagine is that inside of a star, there are trillions and trillions of these little particles, and they're all doing this wiggling. And the combination of all that wiggling is just all these waves that are coming out that we eventually see from our perspective. So pretty fun to play with. Definitely very hypnotizing. What did I leave? No, there's nothing else you can really do. The rest of them don't really do anything that impressive. One thing I noticed, though, is that compared to when I was able to play with this before, when you run it in this Flash player thing, you can really do some very strange things with the system that you couldn't do before. I guess because previously it was being run on the internet, but now it's being run on my computer. So I could never make these kind of waves like this before, but now you can. It seems pretty fun to play with. Anyway, so there we go. That's our radiating charge example, which is supposed to tell us how it is that electromagnetic waves are produced by little tiny charges that are oscillating around. All right, so let's get into today's lesson. So today what we're talking about is inductance. It's actually connected to what we were just talking about, but the way in which it's connected won't be immediately obvious. We have to do some understanding of what this is, and then from there we'll eventually be able to see how it is that these are connected to waves. Okay, so suppose that I have a circuit, and we just start off with a really simple circuit here. Let me draw it kind of as if it was like three-dimensional. So I start off with a battery. We'll just have a normal standard DC type of EMF source, positive on this side, negative on this side. And our circuit's going to kind of come this way, and it's going to go this way, and we're going to have in our circuit a switch. And I guess I'll put a resistor in here. I don't have to put a resistor in here, though, do I? I don't think I need to put a resistor in here. We're just going to have literally just an open circuit like this. So we have a circuit. All it contains is a switch and an EMF source, right? But it is a loop. Now, if we close the switch at time equal to 0, then what's going to happen in the circuit is that the current in the circuit is going to grow from 0 up to some value. You know what? I'm going to put a resistor in here just so I can click on this. I'm going to put a resistor in here just so I can talk about what happens with the current in terms of variables. So let's say there's a resistance to the circuit that we call R. Okay, so the current is going to grow from I equal to 0 up to I equal to E over R, right? Over some time interval. And it's probably going to be a very, very short time interval. Probably on the order of nanoseconds. But nonetheless, the current starts at 0 when the switch is open, and then when the switch is closed, current is going to be flowing through the circuit, right? So let's look at what happens when that's going on. The current goes from I equal to 0 up to some value, and it takes time. What that means is that as a result of this, the flux through the loop is changing. I should be more clear here. The magnetic flux through the loop is doing what? What is it, increasing or decreasing? Oh, maybe I should be more clear about this. When we close the circuit, there's going to be current flow, right? Like this. And that current flow produces a magnetic field, right? If the current's flowing out towards us this way, then the magnetic field lines are going to look like this. Right? Those are the magnetic field lines that will be created there. On this side over here where the current flows this way, the magnetic field lines would kind of be coming up and around like this. Right? Over here where the current's like this, the magnetic field lines are going around like that, just based on the right-hand rule. So we know that magnetic flux through the loop is increasing, right? Well, I didn't. I was going to ask you to say, but then I just went and said it. If the current goes from 0 up to some value, which means the magnetic field goes from 0 up to some value, then would you all agree that the magnetic flux through the loop is increasing? Do you all agree with that statement? Okay. According to Faraday's law, there has to be an induced EMF then, right? There's going to be an induced EMF in the loop that opposes this change. So in order to have an induced EMF that is going to oppose this change, it is going to have a direction opposite to the current, right? So on here in a different color, maybe this color here, we're going to say there is going to be an induced EMF, sometimes referred to as a back EMF, or an induced current. Wait, what am I writing? I induced. That is going to oppose the buildup of current in the circuit. So to put it simply, this circuit, by virtue of being made into the form of a loop, has a magnetic flux that's increasing through it, and so there needs to be an induced EMF that opposes this increase, okay? This will produce, so this induced EMF that opposes this increase will always be in the opposite direction. Will always be opposite to the EMF of the circuit, to the EMF of the power supply, to the EMF of, you're right, I don't know why you deleted that, but it's because of Lenz's law too, Haiti, that's correct. To the EMF of the, this will always be opposite the EMF of the power supply. Okay, so the effect of this, oh, that's okay, I understand. The effect of this is that the current cannot instantly go from 0 up to this. It has to happen over some short time interval, because the attempt of the circuit to put current into the circuit creates a magnetic flux that opposes that attempt. So as a result, you get this induced EMF that goes backwards. We call this effect, we call this a back EMF. There's two names for it. We either call this back EMF, which I like this word, or self-induced EMF, because it's being induced within the circuit itself, right? So this circuit is inducing an EMF within itself that makes it so that the current can't grow instantly from 0 up to its maximum value. We call this back EMF or self-induced EMF. And we call the kind of process self-induction, you might say. Okay, it looks like things are being cut off there, but nothing's being cut off right now. Yeah, we call this process self-induction. All right. And we could even design a circuit whose whole purpose was to magnify this effect, right? What would that circuit look like? Well, if we had a circuit where I took a battery, like a power supply, so we got our EMF, and I hook it up to, let's say, a solenoid, for example. So let's say we put a resistor in here. So resistor R, and then in my circuit, I intentionally put a bunch of coils, right? So I make my circuit have within it some part that has a bunch of coils inside of it, and then we put a switch in here, right? So say this is like a lot of coils, maybe even like a solenoid or something like this. If I put that into my circuit, now what happens is that if I close this switch so that a current flows in the circuit here like this, that same current is going to flow through the pieces of the solenoid right here, right? And because of the solenoid's nature, the magnetic flux through the circuit is now going to be much, much bigger, right? So with the solenoid, the change in flux is going to be much more drastic. Okay. We'll get to that in a second, Evan, but you're right, it would. Well, we're going to talk about that in a second. Right now, we're just talking about closing switches so we can keep things simple, and then we'll talk about what happens when you open the switch, but you're absolutely right. Opening the switch would cause a decrease in flux, and the circuit would actually make it so that the current wants to keep flowing. Anyway, so with the solenoid, the change in flux is going to be substantial, and as a result, the current is going to take much longer to actually reach its maximum value, because now the self-induced EMF is going to be even bigger, right? So in this case, our induced EMF is going to be back this way. Our induced current, you might say, is going to be back this way. But in this case, the induced current is going to be much larger, and so this effect is much bigger. And as a result, what's going to happen is that this circuit is going to take a very long, well, not a long, very long time. The circuit will take longer to reach maximum current. Because the induced EMF, or the back EMF, will be bigger. And why is it bigger? It's bigger because the flux through the solenoid the change in flux through the solenoid will be larger. Does that make sense? You're going to get an even bigger back EMF when you put a bunch of coils in here, because now the change in flux is bigger because you have more loops here, right? Because remember, the EMF that's induced, according to Faraday's law, is negative in d phi dt, right? So if I add more loops, then the number of loops that I add to my circuit will directly increase the back EMF, right? So does this conceptually make sense to you all? We learned about Faraday's law. We learned about how if you move a magnet near a coil, it'll induce an EMF. That EMF will create current in the coil, right? Here what we're finding is that any circuit has this nature that because of Faraday's law, if you try to instantly turn the current on, the circuit is not going to let you do that. There's going to be an amount of time that's going to lapse before you reach maximum EMF, and it's because the act of turning on the circuit leads to a flux through here, and the magnetic flux through these coils induces an EMF that's going to be opposite direction to what's going on in the circuit. Okay, does this make sense? Okay, so switching circuits on and off and on and off and on and off does have an effect on the circuit, and the current does not instantly reach maximum value. So the way that we measure this, the way we measure this quantity that we call self-induction and how much back EMF a circuit is going to generate is through something that's called self-inductance, okay? So we can we can quantify how much a circuit what's the way of putting this? How much a circuit, let's do it this way. How much back EMF a circuit will generate. And we do it through something we call self-inductance. We use the symbol L for this. I don't really know why. This is our symbol for self-inductance. And I'm not going to derive this, but I will give you an example of why it works. So the self-inductance L, there is a way of deriving it, but it's not particularly illuminating. We basically just use this equation. The self-inductance L is going to be defined by the number of turns in our circuit multiplied by the flux through the circuit and then divided by the current flowing through the circuit at any moment in time. Okay. And I'll just give you an example of how this is used because I think it makes a lot more sense when you see an example. But we call this self-inductance. Okay. Just to show you the way that it works out, for example, for a solenoid, we're going to find the self-inductance of a solenoid. And I hope this will help you to understand why this definition makes sense. The reverse that I could have done was I could have set up a circuit and I could have tried to figure out what this quantity was, and then I could have named it self-inductance, but I think that kind of is somewhat circular. So suppose that I have a solenoid, okay, so we take the normal way we think about a solenoid is you take like some kind of a tube. Just to remind you what a solenoid is, it's just a tube that has wires that are wrapped around it like this. I'm not going to draw like a whole lot of rings, but the idea is we've got one continuous wire that is wrapped very tightly around our object here. So the coil comes out like that, and it comes out on this side over here. Let's say the current flowing through our system at a moment in time is defined as I. So we have the current that flows through this like this. Let's say that the length of my solenoid is L in this direction. Let's say the cross-sectional area of an end cap is A. And we can then say that with the direction that the current's flowing there, there's going to be a magnetic field that's produced here. Just, can you all tell me? Oh, it's Linz. That's where the L comes from? Okay, that's good to know. So maybe Linz came up with this concept. Or is named after Linz, either way. Okay, thanks, Justin. Okay, so if the current is flowing in our solenoid like this, can you all tell me, is the magnetic field pointing to the right, or is it pointing to the left in this case? Doesn't really matter for this, but it's always good to kind of just check to see if you're still paying attention. Left, yeah. So we're going to get a magnetic field here, and it's going to tend to point in that direction there. And then what we can do is we can say, we know what the size of that magnetic field is going to be, roughly. The way that we've talked about these things is that we take mu naught, and you multiply by the number of turns divided by the length of the solenoid, and then you just multiply by the current flowing through the solenoid I. Right? So that's the size of the magnetic field. So now let's calculate the inductance L, self-inductance. I'm just going to be calling this usually inductance, by the way. But self-inductance is really what it is. Okay, so the inductance L should be equal to the number of turns in the coil multiplied by flux. Flux is just magnetic field multiplied by area divided by the current flowing in our system. So this is going to be N times magnetic field is given by this expression here for a solenoid. I really shouldn't have that one there. There we go. Mu naught N over L times I. We divide by I. Oh, there's an A in here too. My bad. That's the BA. So you can see that the currents cancel, and we end up getting that the self-inductance of a solenoid is equal to mu naught N squared divided by L times the area. There we go. That is our self-inductance. If we had values for mu naught, N, A, and L, we could come up with a number. So let's go ahead and do that. So let's say we let the number of turns on our solenoid be equal to 1,000. We know what mu naught is. Let's let the length of our solenoid be like 25 centimeters. And cross-sectional area. So let's say that it has a radius. Let's say what the radius is. That way we can use that. Let's say the radius of the area, R, is like half a centimeter. We'll use 1 centimeter. Okay, so let's say that these are the dimensions of our object. Let's calculate what L is equal to. So L is going to be mu naught, which is 4 pi times 10 to the minus 7 Tesla meter over amp, times N squared, which would be 1,000 squared, divided by L, which is the length, which is 0.25 meters. And then we multiply by the area, which will be pi times the radius squared, so 0.01 meters squared. And this is going to give us our inductance, or the self-inductance of our solenoid. And what this is a measurement of just how much our solenoid is going to resist our attempts to turn the current on or off. Put it in a more specific way, it's going to tell us exactly how much this solenoid resists the attempt to change the current. So I got 1.57, 1.58 times 10 to the minus 3. And we'll look at the units. The unit of inductance is what we call the Henry. So it would be 1.5 times 10 to the minus 8 Henry. The symbol for the Henry, the right-hand rule, Haiti, you wrap your fingers around the direction the current's flowing, which is like this. Your thumb points to the left. That's the direction of the magnetic field. You can kind of review the right-hand rule in many places on the internet or in the book. Okay, so this would also be written as 1.58 millihenry. Okay, so the Henry is the unit that we use for inductance. And what is 1 Henry equal to? Well, we can figure it out from here. That if we look at the units, you're probably using your left hand if you got the other direction. You have to use your right hand. So the units of this are Tesla meter per amp times meters squared over meters. Did I get it right? Well, Henry is a last name, actually. I know what you mean, but Henry is actually the person's last name. He was an American scientist. I don't know what his first name is, but Henry was his last name. He was working on the same stuff that Faraday was working on, and I think in some older textbooks they refer to Faraday's law as Henry's law, because I think he also figured out the same concept around the same time. So it looks like what we get is Tesla meters squared divided by amps, right? Because one of the meters cancel. This is what we have. So what's this equal to? I guess there's a couple different ways to reduce this down. Probably the easiest way to get to base units would be to change Tesla into, so 1 Tesla is equal to 1, I think it's Newton per meter amp. I don't know why I wrote it that way, meter times amp. So this would then be Newton over meter amp times meters squared over amp. So we're going to get Newton meters over amp squared. Ugh, did I do that right? I think I did it right. We could then reduce this even further into I don't want to put it in regular units. I'm going to write this as joules per amp squared. Just because. This isn't very useful either, because what I'd like to do is to get it in terms of some units that are all electrical units. So let's try a different way of going about this. A joule over an amp is equal to a joule divided by a coulomb per second times an amp, right? But this is equal to a joule over a coulomb is a volt, right? If I move to the second to the numerator, we get a second right here, and then we divide by an amp, okay? But what's a volt over an amp equal to? That's resistance unit, right? If you don't remember, delta V equal to IR. So a volt divided by an amp is equal to 1 ohm. So this could also be written as ohm seconds. This is going to be the way that we want to remember this as, because this will be 1 Henry is 1 ohm second, okay? That is, I think, the best way to think about it, right? 1 Henry is 1 ohm second. Okay, but what is it really? What does a Henry measure? It is going to measure how much your circuit is going to resist your attempts to change the current, basically. That's what it's going to do, okay? Now, let's I want to look at this equation right here. Okay, I want to write one more equation down for you now. So, knowing what this thing is, okay, what we're going to do is we're going to say that the back EMF, or the self-induced EMF, is going to be equal to, we'll call it E, and it's going to be equal to negative L multiplied by the time rate of change of current in the circuit. Okay? You're supposed to compare this to the two other types of EMFs that we've learned about, which are E equal to IR. Let me write it like this. E equal to, we'll write it as R times I. And what's the other one? The Q over C, right? Okay. So we've got these three equations, right? We've got Ohm's law, we've got the relationship for a capacitor, and now we have this self-induced EMF thing, and I want to show how they're different from each other. So in the case of Ohm's law, which I think is the easiest one to understand, Ohm's law says that if I place a resistor into a circuit that has an EMF, right, that tells me exactly how big the current I'm going to get out of it is, right? So for example, if I have an EMF that's 100 volts, right, and I attach a resistor that has a value of 0.1 ohms, right, that gives me a current of, 1,000 amps, right? But if I were to double the size of the resistor, right, if I took 100 volts and I cooked it up to a resistor that was 0.2 ohms, so twice as big, now I get a current I that's only 500 amps, right? So what you could say that a resistor does is that for a given EMF, the size of the output current is going to depend on how much resistance there is in the circuit, right? The more resistance, the smaller the current. That's a very simple thing to understand, right? You put more resistance in, you get less current out, right? So how does that work with self-induced EMF, okay? The self-induced EMF equation states, if we just ignore the negative sign for a second, let's just talk about the absolute value. The negative sign is there to represent that when the current increases, the induced EMF is opposing the current, and when the current decreases, the induced EMF is going to be in the same direction as the current. But let's just talk about the absolute value of it, and let us divide by L. This is then equal to di dt. So what this tells us is that the bigger that the value of L is, right, the smaller that the rate at which the current builds up is going to be. You can think about this as being the rate at which the current builds up in the circuit over time. Okay, so assuming we have a very simple circuit that only contains, like for example, this inductor here, okay? So let's say that I have a circuit. I've got an EMF E, let's make it equal to 100 volts, right? I put a switch in the circuit and I put into here something that I'm going to call this an inductor. This is the symbol for an inductor. It just looks like a bunch of coils like this. And we use the letter L to represent that we have an inductor there. Okay? So suppose I have a circuit like this, and I close the switch here, and I ask the question, how long does it take for the current to build up? Okay? Well, you take E over L. So if we take the value of L that we just calculated, which was 1.58 millihenry, right? And we plug into the top the EMF of 100 volts, right? Then we get di dt, in this case, is going to be equal to 100 over that. And we get this number. Now it's a huge number, okay? So I'm just doing this as an example. This doesn't really mean anything because, well, it does mean something, okay? All right, so that is going to be equal to the rate at which the current builds up in the circuit, right? So now, we kind of need a resistor in the circuit, don't we? So what if there's all kinds of things that I'm leaving out of this story here because I want to simplify it as much as possible. So let's ignore the fact that there's no resistance in the circuit for now and just assume that that's okay. What do you get? 63.3? This is milli right here. So you need to divide by 0.00158. That's okay. All right, so let's say that we just set the maximum current, right, equal to 10 amps. Okay, let's just say that's what our maximum current in the circuit is. That would imply that there is a resistance of about 10 ohms, right? So let's let Imax equal to 10 amps. We could ask the question, how long to max current? And the answer would be, well, you would just take, you could say the current in the circuit is just going to be equal to the rate at which the current builds up multiplied by the time. So if we take 63,000 amps per second and we divide by, other way around, my bad. Shouldn't skip steps. If I take I divided by the buildup of the current, which is di dt, that's going to be equal to the time. So this would be 10 amps divided by 63,000 amps per second. And so we get a very small number, obviously. That's the point, though. So if we take 10 and we divide by 63,000, we're going to get 0.16. 0.16 times 10 to the minus 3. I'll put 0.16 milliseconds is what we're going to get. I think if I did that right. Yeah. 0.16 milliseconds. This would be the time that it would take. So if we close the switch after 0.16 milliseconds, a time that is almost imperceptible, right? For humans, that's how long it would take for the current to build up. Does that idea make sense? Yeah, okay, so the idea is that if we close the switch at time equal to 0, the effect is going to be that there is going to be an EMF set up in the circuit. Because there is a magnetic flux through here, there's going to be something that we call a back EMF. So the normal current would flow this way. There's going to be an induced current that flows the opposite way, what we call the back EMF. I induced, back the other way. As a result of this induced EMF, it's going to take time for the current to build up to its maximum value. Okay? And in this case, if I tell you that the inductance of my circuit is equal to 1.58 millihenry, and I tell you the EMF is 100, then if we take 100 divided by this, we get 63,000 amps per second. This is the rate at which the current is going to build up. If I tell you that the maximum current is 10 amps, then if I take 10 amps and I divide by the rate at which the current builds up, it'll tell me the amount of time that it takes for the current to reach maximum. So this is the time to max current. That's what that represents. No problem. Does anyone else have any questions about what's going on here? So now we can quantify the difference between this circuit and a circuit that has a larger amount of inductance, right? What would happen if I double the inductance here? If I make the inductance here twice as big, what's going to happen to this number? So if we do 100 over 2 times this, it's going to get smaller, right? So instead of 63,000, it'll be something like 31,500, right? What's going to happen to the time, though? So if we increase the inductance of our circuit, we decrease the rate of current buildup. And what does that do to the time over here? It's going to double it, right? If I double the inductance, it takes twice as long. That's all that an inductor really does, is by adding more and more inductance to your circuit, you're making it take a longer time for the current to build up to maximum, right? All right, so we have some understanding of what this inductor is doing. We're going to look at some animations of this here in a second as well, but I want to come back to my solenoid right here, where we actually found the inductance of the solenoid itself. We'll get to some real-world examples in a second, Evan, yeah, but I don't want to... I'm going to go kind of piece by piece. That's kind of what we'll do next, basically. All right, I want to look at this, though. So the inductance of the solenoid, right? What does it depend on? Well, it depends on magnetic permeability. So this number could be actually altered. It can be made bigger or smaller. Well, not smaller, but it can be made bigger by making the core of our solenoid out of iron, for example, something that has a larger magnetic permeability than free space. So we can increase inductance by putting like an iron core inside of here, for example. That's one way we can increase inductance, okay? Other than that, the only way to increase inductance would be to change the number of turns in the solenoid. What happens to the inductance if I double the number of turns in the solenoid? Keeping all the other things the same. What happens to the inductance if I double the number of turns? It quadruples, exactly. By doubling in, you get 2 squared, so you get a 4. So doubling the number of turns will double the inductance. We can make the area of the solenoid bigger as well, right? Make this fatter. And we can make the length shorter. So really, if you want to get the ideal kind of shape of your solenoid that's going to produce the most amount of inductance possible. So if your goal is to just take some length of wire and construct something that's going to have the largest amount of inductance, what you would want is an object that is kind of wide and has coils that just wrap right on top of themselves, almost like a donut. Almost exactly like a donut, basically. In fact, the more I draw this, the less it becomes clear what I'm trying to draw. But from above, what it would look like would be something like this. Just a bunch of coils wrapped as tightly as possible, as many as you possibly can get, like this. And if you look inside of almost any type of circuit, like look inside of like an amplifier, open up your computer, open up a radio, you will find inside of those devices are stuff that look exactly like this. These coils of wire that are wound up into donuts inside of your circuit, little tiny coils. So self-inductance is really, okay, it's really a measurement of how many coils you have, right, in, how fat those coils are, and how skinny the kind of like thing that you made is. That's really, when we talk about inductors, the word, so when I point to this thing in a circuit here and I say this is an inductor is equivalent to a coil, okay? These are the same thing, basically. We use the word inductor because these coils are really good at inducing EMF in themselves, right? At self-inducing an EMF. And that means that they help to, this is kind of an answer to your question, Evan, they help to smooth out fluctuations in current in the circuit. They prevent the current from suddenly spiking up to some value or suddenly falling from a big value to a small value. Yeah, you see them inside of power supplies that you've opened up, exactly. They help to smooth out fluctuations in current. That's ultimately what an inductor does. So I'm just going to write that down. Inductors, because of this relationship, right? E, we call it E sub L. We'll use that kind. This is kind of how we're going to write this in the future. EL is equal to negative L di dt. So inductors tend to smooth out fluctuations in current. They do other stuff too, but this is just one of the things they do. They don't keep it constant, but they tend to want to keep the current doing what it's already doing, basically. If there's no current, it wants to keep the current at zero current. If there's a lot of current and you want to turn the circuit off, they're going to keep the current flowing. Okay, that's the other half of this, and it relates to a question that... was it you, Evan, that asked what happens when we turn the circuit off? Yeah, opening the switch to decrease the flux. Exactly. So now if we look at the opposite situation, which is if this quantity is negative, right? So if we're trying to go from a current, let's say, that's equal to 10 amps down to a current that's equal to 0 amps, right? Then di dt is going to be negative. And so the self-induced EMF is actually going to make it so the current wants to keep flowing, right? So this is how an inductor or a solenoid can act as an energy source. They can act as an energy source. So if we think about the following situation, let's say we have a circuit, and within our circuit what we have is a solenoid here, so an inductor. We have a switch that's already been closed for a long amount of time, and we have an EMF source here. And let's say now what we do is we open the switch. Okay, so now what we do is we open. This is the one I have a hard time drawing, because now what we need is another portion to the circuit. So let's add that portion up here. Forgot about this. Okay. No, this one can be closed at the top, actually, can't it? All right. So let's say I have a circuit, right? I have current that's flowing in this direction. Here, I. It goes up, it flows through my solenoid. And of course, it's also going to be going up through this outer portion here. I know there's no resistors in here, so it's kind of weird, but as a result of the current flowing through here, we're going to get a magnetic field, like this right here. And now what happens is we can ask the question, what happens when we open the circuit? Okay, so this has been closed for a long time, but now we have opened it up, okay? We'll say it opens at t equal to 0 or something. Now what's going to happen is that the solenoid does not want the current to suddenly disappear. So it is going to keep pushing the current in the same direction. And what will happen is the current flowing through the outside portion here, well, I guess I can leave it on there because that's the conventional current I, right? We'll just call that I. Now what happens when you open this is that the magnetic field in this is going to start to decay, but it can't decay instantly. So it's going to produce a self-induced EMF back in this direction. So now there's going to be an induced, There's going to be an induced EMF in the same direction as what it flows. Yeah, which is this way, right? So back this way. And what that's going to do is it's going to make it so that the current flowing through the solenoid goes in the same direction as it was before until the magnetic field slowly decays away. And depending on the size of the solenoid and the size of the magnetic field that was there, it could take longer or shorter for the current to decay away. The point is that an inductor is going to stop you from trying to instantly increase the current. It's also going to stop you from instantly trying to decrease the current. How much time do we have right now? Do I have time to show you one of these kind of FET demos? I think we do. So let's see what this looks like physically. If we were in the lab, I would show you demos of this, but okay. PHET. And now we want to go to, oh, it's already open here because I was showing things to my other class. All right, we want to look at these things. All right, so what we want is the AC construction kit. And I think this one still works because I remember using it last time. I say that, maybe it doesn't work. All right, here, this one. Download. It's a Java file, that's probably a good sign. Means it'll probably run. My memory is that this thing does not work well with inductors, but we're going to give it a shot. So we take our wires here. We are going to throw into our circuit a switch and an inductor and a light bulb so we can see the current. And then probably going to want one of these too. Need a battery. And I'm guessing that's probably all we need. So a very simple circuit. We're just going to have a switch, a light bulb, an inductor, and some wires. Okay. I'll go ahead and do that. This thing is going to measure our current flowing through the circuit. Alrighty. And maybe at some point we might want one of these dudes. I don't know. We'll think about it. Right click for options. You got it. So what do we have here? What a power block does for computers and stuff to print. It has to be part of it. There's going to be other things within it as well. There's a lot of ways to stop physical computer power supplies. At least the PFC coil is just used as the pressure to balance out. Yeah, exactly. Sometimes it's referred to as a magnetic ballast. Like in engineering textbooks, it might be referred to as a magnetic ballast because it acts as a way to balance out and slow down fluctuations in current. Okay, because like you could damage the system if the current suddenly jumped to a certain value. It could cause damages into your system. So, all right, so let's see what happens now. The switch is open, so nothing happens. But can you all tell me? Can you make a prediction of what's going to happen here based on what we said? So we've got our inductor here. We can look at the value. It has a value of 50 henries. I'm just going to tell you that in your homework, you're always going to see things that are in millihenries or microhenries. 1 henry is a huge amount of EMF. It's just a huge amount of EMF. Oh, no, I'm sorry. Self-inductance. Anyway, nonetheless, we've got an inductor of 50 henries here. We have a resistor that has a resistance of 10 ohms. Can you all tell me, what do you think the light bulb is going to do when I close the switch? I'll tell you what, we're going to do something else first. Let's connect this up. What happens when I close the switch? The light bulb comes on instantly, right? What happens when I open the switch? If I can do it, the light bulb goes off. So on, off, on, off, on, off. This is a circuit that has 0. In fact, you can see it here, right? This is really important to look at this here. If I switch on, switch off, switch on, switch off. You see how it's a step function? Step function is something you're familiar with, right? Is it something you're familiar with? We go from 0 to something, from 0 to something, from 0 to something. It's instant, right? Step function. Oop. Goes up and then down, up and then down. So what is going to happen when I put the inductor in here? What is that curve going to look like? And what is the light from the light bulb going to look like? Will the light bulb light up instantly? It actually won't, Evan. We're only going to be focused on the on portion of this. In order to do the off portion, I'm going to have to add pieces to the circuit. Okay, you think the curve here is now going to be more smoothed out? And what are we visually going to see with the light bulb? Is the light bulb going to instantaneously reach max brightness, or will it take time to reach max brightness? It's going to slowly light up. Okay, so let's watch this. So here we go, closing it in 3, 2, 1. So gradually the current is building up to its maximum value. Slowly the light bulb is reaching its maximum value. And after some amount of time, that I can tell you right now is going to be proportional to L over R, this divided by this. Remember that a henry is an ohm second, right? So if I take henries, 50 ohm seconds, right? And I divide by ohms, I get seconds, right? So presumably, that's going to be some kind of measure of how long this takes. Let's see if that's true. Now, in this case, it is going to instantly switch off, but this object is actually still charged, I believe. So we're going to discharge it. We'll talk about what it means for it to be charged. By it being charged, it means that it just has some current flowing through it. Okay, so now if we look at this, I wonder if it takes 5 seconds. Now, 5 seconds is going to be the time that it takes to get to 63%. So to get to full, it's going to take something like 5 times that. So 25 seconds is what it's supposed to take here. Let's see if that's the case. So if I turn this on right at like 280. So if this should go up to about 25 plus 280 would be 305, right? It should take till about 305 until we've reached maximum here. Maybe a little bit sooner. The max current in our circuit is going to be 9/10, and we're basically there at 90%. About 305, maybe a little bit sooner, but it's only so much. Oh, look, it's still just suddenly increased. So I think now it's at maximum current. In fact, we can check to see if it's at maximum current here, probably by putting our device around here. Yeah, we're at maximum. We're not quite there. We're pretty close though. Okay, so let's open that up again. We drop to 0. Let's discharge our inductor. Now, the next thing we want to look at is how increasing the inductance changes this effect, right? Or decreasing. So let's say let's just go with decreasing, because I think this is the biggest value we can use. So if I decrease this down to 10, so now there's less inductance, which you can't see it here, but what does that mean? That means that we have less coils of wire to work with, right? Maybe we've taken our entire thing and we've cut it into a fifth. So we have less inductance now. What is that going to do to the rate at which the light bulb lights up? If I decrease the inductance of the circuit, and again to remind you, inductance is a measurement of how much the inductor is going to resist your attempts to change the current. So if we lower this, should it light up faster or slower? Light up faster. Exactly, that's right. So let's check it. So if we close this now, you see the curve is much steeper, and we're going to reach our maximum value much faster. There we go, almost there already. So just to compare the two, if I change the inductance to 50 again, right about there, and we close this, it's very slow. It's almost like the circuit is now slow to speed up, right? It's slow to reach its maximum speed, right? It's just like when you're in like a sports car, right? Something that's really small with a really big engine. You can get from 0 to 60 very quickly, right? But if you're driving around in like a semi, like a diesel engine, like a big, like an 18-wheeler or something like that, it takes much longer for the diesel engine to get up to maximum speed because there's so much more mass to move, right? So the way that I think about inductance is it kind of endows the circuit with a type of mass. When you have high inductance, the circuit is really sluggish. So that means that it is hard to change its direction. So just as an example, I'm going to use my mic right here. I don't know if this is a good example to use. No, let's use the textbook. That's a good example to use, the textbook. So if I take my textbook right here, and I try to move it around, right? I try to change the velocity of my textbook. The textbook is going to kind of tend, like when I move it in one direction, I try to slow it down. The textbook wants to keep going in that same direction, right? So if I take my textbook with one hand, I don't even know if I can do this. I'll try though. If I take my textbook with one hand and I try to move it back and forth like this, it is very difficult to do so. What's the reason for that? Why is it hard? Actually, it's easier if I grab it from the bottom, I guess. If I take my textbook and I move it back and forth right here, why is it hard to turn it, to change its direction compared to picking up something like this pen, where if I move it back and forth, it's very easy to do. It's inertia. That's the right answer. The right answer is inertia. Or Newton's first law, also the right answer. Exactly, because massive objects have more inertia, right? They tend to be more sluggish with your attempts to change their motion, right? So what happens here is by putting this inductor in the circuit, right? Let's look at it again. It makes the electrons themselves more sluggish. They do not speed up instantly, right? They have to kind of slowly be pushed and pushed and pushed and pushed and pushed and pushed until they reach their maximum speed. And once they reach their maximum speed, right? Now we can show you the other half of this. They don't want to slow down anymore because now they've already got a lot of inertia, right? So a circuit without, here, let's get rid of this dude. A circuit without this is like a massless particle, okay? A massless particle, it has no resistance to motion, so I can take a really light object and I can instantly speed it up to a very high speed, something like an electron. Just go from this speed to this speed. On, off, very quick, instant, right? So by adding the inductor in there, we've basically, in a way, kind of increased the mass of the circuit. That's at least the way that I think about it. So inductance is very closely related to mass, if we were to compare it to something from Physics 1A. Now let's see if I can show you the other half of this, which is the turning off part. Let's see if we can do that properly. Making some room here to expand our circuit. So now we'd like to prove that the circuit also tends to keep the current flowing. So we're going to take this, we're going to take this, We're going to take this. We're going to take this. Sometimes this doesn't work very well. And I don't know what the reason for this is, but I think this should work. I'm pretty sure this should work. Can I get another current chart over here? The current right here. Alrighty. I'm pretty sure this is going to work. Alright. Close the circuit. This is a nice view here, by the way, if you look at this. Notice what happened here? The top one came on instantly, right? But the one in the segment with the inductor doesn't come on instantly. I'll show you again because I did it very quickly there. Okay, this is working. This is great. All right, we'll discharge the inductor. Okay, so we've got zero current in both branches, right? So the first thing to watch is what happens to both of these light bulbs here when we close the circuit. Top light bulb comes on instantly. Bottom light bulb takes time to come on because this segment has inductance, right? A lot of inductance. It's got, again, 50 henries of inductance. Now give this a little bit of time. We can check our voltages here. This one should be 9 volts already. This one here should also be 9 volts pretty soon. It's getting there. We'll wait till we get to absolute maximum now. What happened over here? Okay, this wasn't working for a second. I don't know why. All right, that's close enough, right? So now watch what happens when we turn it off. The idea now is that this object has a magnetic field, right? This inductor, so it's got a magnetic field and then it points this way. That magnetic field is a source of energy in the same way that the electric field that exists inside of here is a source of energy. And so that source of energy cannot go away instantly. In fact, it takes a little bit of time. And what's going to happen is that by trying to turn the current off, this thing's going to say, no, you can't just instantly turn the current off. I've still got this big magnetic field, and it's going to have to keep going. If you use the analogy of mass, you would say, okay, well, these particles can't just suddenly stop flowing. The particles that are flowing through this piece, at least right here, have a lot of inertia. This is the weird part about this, right? These electrons have like no inertia, but these electrons that are flowing through this piece effectively do have inertia. That's how the analogy works. And so as a result, if these ones have no inertia, they're like really light particles, but these ones are like bowling balls, right? So this is like a circuit where you've got bowling balls running through here, through this guy, right? And you've got a bunch of, let's say, ping pong balls coming here. And you all know what happens when a ping pong ball hits a bowling ball, right? What's going to win that battle? It's going to be the bowling ball every time, right? No matter how fast the bowling ball is even moving, even if it was at rest, a bowling ball moving very slow has a lot more momentum than a ping pong ball. And right here, they're basically colliding with each other. You know? Can you see that? Because the electrons here are going this way, and the electrons here are going this way. So when we open the circuit, these electrons have like more inertia, and so they're going to push it the other direction, right? So we'll watch what happens. I'm going to open this in 3, 2, 1. What you want to look at is what happens to the direction of flow here at the top, and what happens to the brightness of the light bulbs. Okay, 3, 2, 1. It happens very fast. It happens very fast. You can do the same thing with a capacitor, right? You can do the same thing with a capacitor, right? Like I could replace this with a capacitor, and what would happen is that the current would basically build up until there's charge on the capacitor, and then when I open the circuit, the current would flow out of the capacitor back through this light bulb, right? So in a very real way, the inductor is storing a type of energy inside of its magnetic field, and that magnetic field can't decay instantly. Does inductance add in parallel? Yeah, it does actually. It's exactly like, yeah. So if you put 2 inductors in series, it's going to add them. So I could increase the inductance here by a factor of 2 by just putting another one in series, and I believe parallel inductors also follow the same rules, yeah. So the inertia is from the magnetic field exactly of the inductor. And again, the key thing to understand here is that the back EMF from the buildup of the magnetic field, when you're turning it on, is opposite to the current, right? But when you turn it off, the EMF is going to kind of tend to stay in the system, and it's going to kind of keep pushing this way. So that's basically what an inductor is, and it's a very important part of electrical circuits. There's also things called diodes. We're probably not going to talk about diodes in this class, but we might. Depends on how far we get. Anyway, so there we go. Again, we open the circuit. See how it instantly changes the direction of these things, and then current falls away. And diodes are neat. Okay, so I think we need to take a break. It's 2:21, so we'll take a break until 3:31, and then we'll come back and we'll do some more discussion of how inductors work and what kind of effect they can have on a circuit. Spent a lot of time just talking about theory here, but I think it's really important because otherwise inductors can seem pretty weird. All right, so we will stop there.